All right, does anyone see my screen? Yeah, perfect.
Yeah, good.
All right, welcome everyone to today's workshop on computer vision. And this is the first part of a neural networks workshop. It is a lot to cover, neural networks. So we couldn't, I think we will run out of time. I have allocated 2 hours anyway. And whatever we don't finish today, we will finish in the future workshops. And basically, what I'm trying to do with my friend here is Isaac, and we will be running more workshops over the coming days. So our focus series in these workshops will be to help you with AI adoption in your business. And it's going to be mostly technical, but my friend will also cover some commercial sides of how you can adopt and commercialize AI in your business or in your research area. So if you're an academic and you've got some ideas, how you can build AI apps and commercialize it through cloud computing. So in today's workshop, we will cover the convolutional neural networks and how to do it in TensorFlow. So my name is Ali. I'm the founder of BML. But I also do instructing as well. And I work for a company currently called Hack Partners. We do we build AI, ML, and data analytics solutions. So basically, and then on the side, I run these meetup group as well, right? Just basically love teaching. So I love run workshops. And what I'm planning to do over the course of the next few weeks or next few months. So this is the plan for the next 6 months. So we've already done one workshop on neural networks. We have a recording of that. I just haven't had the chance to upload it, but I will do. In that one, I will go into the details of how neural networks work, like fully connected neural networks, and how it works around the math size part of it. In today's workshop, I'm not going to go into the maths much. The focus of today's workshop is just going to be helping you get the intuition of how convolutional neural networks work, and why we go from fully connected networks to CNNs when it comes to images, and how images are stored in a computer and those kind of things, right? So today's focus will be on image classification tasks. In the future workshops, we will go into object detection, semantic segmentation, and then style transfer, which is basically, I'll give you some examples of them. And if you want to learn more about TensorFlow, there is a really nice TensorFlow tutorial on Microsoft Learn. So if you search TensorFlow fundamentals, there's some really good stuff on the basics. I will go through some basics with you today as well. And after the computer vision stuff, we will also do a workshop on how you can prepare your images and videos for processing through your models. And then another workshop on cloud computing this time. So how to set up databases, how to set up Azure functions, things like that, streaming analytics. And then we will do another workshop on data streaming. We will actually build a proper cloud-based app where data streams from a bunch of sensors, IoT sensors, and then you do some stuff on it, and then it goes into an AI model, and then you build a dashboard on top of everything. Then another workshop on clustering. We do that instead of Azure, we'll do it on AWS. So you also get exposed to AWS. So with that one, you cluster UFOs, their sightings and stuff with machine learning. So you use K-means algorithm on that one. Then we have, then we'll do another one on MLOps. So we will basically try to classify color images with CNNs on Google Cloud and deploy the training onto cloud. So because transfer learning requires really big, massive networks to train on a bunch of images that are very, a lot of images, my laptop wouldn't just handle, I wouldn't be able to handle on my laptop anymore. We need GPUs for that. So we're going to do it on the cloud, with Google Cloud. Then I'm going to answer your wishes and try to do some NLP afterwards. So we will do some natural language processing and time series data analysis. So for those workshops, if someone wants to volunteer to do NLP workshops, feel free as well. We always look for more speakers. And then at the end, there's also, we want to cover some big data engineering as well. So if you have worked with data analysis like pandas and NumPy, I think we will also do some workshops focusing on data science and just wrangling data sets and working with big data, basically. So before I go forward, does anyone have any questions I know Marcin has one, which says, where can we find the recording for the first session? So Marcin, I haven't actually uploaded it, so it's on my bad. It's literally on my laptop, on my desktop. I will need to upload it and share the link with you. So I'm basically building a page where I will basically share the link to the page, and then you can find all the recordings on there, one after another.
Hi.
Yeah.
Can I ask a question from a microphone?
Yeah, fine.
Yeah, I was just going to ask, when do you think that this schedule will be happening? Is it on a weekly basis, bi-weekly basis, monthly basis?
It's bi-monthly, so it's every 2 weeks. So the next one will be in 2 weeks.
Okay, cool. Thank you.
Yeah. So I need time to build these, basically build this workshops, because sure. I don't want to just do slides. I want to actually help you get code. So what I'm going to do as well is at the end of this workshop, I want you to implement a couple of popular CNN architectures yourself.
Cool.
All right. Right. So by the end of today's workshop, you should have enough confidence in order to go into, like, I don't know, implement GoogleNet yourself or VGGNet or something like that. We will cover those.
We'll see.
But we'll see. Yeah. I mean, I'm not going to go into maps though, so don't worry. Hopefully it will be interesting. So what we're going to do today is we're going to understand how convolutional layers and convolutional neural networks work. I'm going to give you an introduction on CNN classifier. So what is a classification task? What is the object detection task? And what is the semantic segmentation task when it comes to convolutional neural networks? What else we're going to do is, have you heard of fashion MNIST? So the fashion MNIST data set. We're going to try to classify basically a bunch of pictures of clothes, but like really small pictures, in using a fully connected neural network, and then show you how you can convert that fully connected neural network into a CNN in TensorFlow. And then we're going to try to retrain the network, but like the network this time is a CNN, not a fully connected network, and see how the performance differs. Then and why the performance could be higher than the other one. And then we're going to look into how object detections work on a high level and how semantic segmentations work on a high level. And then at the end we can discuss how you can actually define your own AI architectures for your CNNs. So that's the objectives of today's workshop. We may not go through all of them, depends on the time. We're 15 minutes in, but basically at like 50 minutes or 1 hour, we'll take a break as well. So you can grab some coffee. And then the way the workshop works is that we're going to cover some concepts, then get into code, run some code and understand it, then get back into concepts, continue more, and so on, right? So basically, what you can do afterwards is you can actually then train CNN models to do stuff like this, which is really cool. Like you can train YOLO, for example, to detect objects in videos. Semantic segmentation, which is basically when you classify every pixel in the image to tell you what that pixel is. Is it a car? Is it the building or whatever? And then, yeah, maybe like running some semantic segmentation on your own images. And in the last workshop, you also learn how to apply style transfer so train a neural network to learn the style of a set of paintings and then apply that style to your image. So you can get that image on the right. So if you're interested in like interior design of your house and you want to improve the interior design, but you don't want to, get someone to paint it, you can literally just get a neural network to do the work for you. So you will learn all of these in I think this is the 4th workshop where we'll go into actually understanding how style transfer works. But I want to talk to you about the AI trends that's happening at the moment. So this is basically the trend of the whole industry. Now, this is most updated in 2018, so it's quite updated. But however, what I believe and my friend believes is that computer vision and natural language processing, they're gonna become more popular and have higher growth. At the moment, the adoption rate is about 5%. Across all AI in the UK, the adoption rate is at like 10%. So, but like a lot of companies are like aiming to increase that. The global average is about 19%. And from the trends we're seeing, it's going to get increased much more. And we're going to see more application and novel applications of AI, not just in process automation, but in like all sorts of things, manufacturing, transport, logistics, healthcare, you name it. And computer vision has like a very big part of it where you could like install cameras to do things for you. You might have a lot of more examples than I showed here, but yeah, like it could be the next big thing. It is the next big thing. So learning it is really good because then you could actually figure out how you can apply it in your own industry. Everyone has a domain expertise in their own industry. They might have ideas of how you can use data in their own industry and use a computer vision with it to implement new novel applications. So that's more about it. Before we get into the details, does anyone have any questions about AI trends? What we've talked so far?
What do you think about transformers?
Transformers, like the cars turning into robots. I think it's possible. Yeah, you've already seen the Boston Dynamic robots. Yeah, they're running around on like obstacles these days now. They can jump around like a normal person.
No, I mean transformers, like like you were saying, like transfer learning, that language models.
Oh yeah. So with those as well. So I think with NLP, that's why I said like NLP as well. So I put computer vision here because the subject of this workshop is computer vision, but NLP as well, and anything to do with like text generation, transformers, and all of those things, they will also be going upright in terms of their volume and growth. Not to say like the others wouldn't, but this is where we're seeing the explosion of the AI, mostly in terms of applications. So, I mean, I'm just going to cover some housekeeping here, which is basically, so what is AI exactly? What we're doing it. So normally in traditional software engineering and just programming, you have some data, you write some logic with these if-else loop statements in your language of choice, and you get the result out of it. So you take an input data, you pass it through your function, you get the output. Now with AI, it's the roles are reversed. You give it the output and you give it the input, and then the AI figures out the function. So here the input is your data. You do some data analysis on top, and then you have some algorithm as well that creates the function for you, and then the function becomes the model or the AI model that then they can use to make predictions on things. So whenever you have an input, you pass it through your model, and then the model gives you an output. So if you want to map the input to the outputs, you use data to do that and the algorithm. That's the whole thing about AI. And in AI has a subset of fields called machine learning and deep learning. Each one is a subset of another. In machine learning, you are more hands-on, so you have to do more data analysis, figure out trends, figure out like correlations, and do a supervised machine learning task with scikit-learn or non-supervised, and you just have to do the feature extraction yourself a bit manually. But with deep learning, you can pass it complex multidimensional data like images or videos, or like it could be also like tabular data, and the AI will figure out the features and does the feature extraction and classification for you, or object detection or whatever. And you don't need to do anything. You just pass it the data, and then you just play around with the architectures and a bunch of other hyperparameters related to the algorithm that trains the model. And that's how you get your thing. That's why deep learning is becoming a big thing. They call it deep because in order for this model to be good enough to make those to have a good high accuracy, you need to like have a lot of layers, right? So that's it basically. So that's the main thing. The reason deep learning neural networks work, it's because they follow the same logic as biological neurons. So each of these neurons in a neural network is represented in a simplified manner of how our brains work. So in our brains, we have neurons that are connected to each other. So let's just focus on one of them. each neuron is connected, like have other bunch of neurons are connected to our neuron and they keep sending signals to it. These signals add up, and then if they reach a threshold, so for example, they call it the action potential, it fires off to the next neuron. And then this whole process works across all of our neurons, and then the signal keeps firing off in certain pathways, and the more that signal fires in certain pathways, the more that pathways become like thicker and thicker and thicker in your brain. And this is, for example, how you learn a skill. Like if you're learning piano, at the beginning, everything is just firing off randomly, but then as soon as you learn the skill a bit better and better, a certain pathways in your brain start firing off more, and then they call it the neurons that fire together, wire together. So those pathways become thicker and thicker and thicker, and then you learn that skill. And then your brain does some other magic, and then you learn and can do another skill without actually thinking about it. Now, those bits, we're not going to go into it because your brain is very complex. Like, I'm not a neuroscientist, but what computer scientists have done is they've taken this logic and they've simplified it into a mathematical formula where you take a bunch of nodes, you multiply them by their connected weights, which is like represented by these lines. You add them all up, and then you pass them through an activation function to add nonlinearity to their algorithm. Otherwise, if you don't add that nonlinearity, that whole function, that whole process is linear. So the only thing you can do is just draw lines across your data. When you add nonlinearity, you can draw like squiggly lines. You can literally like do anything with, like, when you try to classify your data or cluster it. So this the whole outputs of neural networks is just to help you to classify data into like different categories. So that's where you add the activation function at the end of each layer or each neuron, so that you can then have a nonlinear process where you can map the input data to the output. So that's just one neuron. And then when you take one neuron and then connect it to the other neurons, that's when you get a neural network, basically. And the maths of it is just basically you zoom out and then you just do that summing functions across all of the nodes, across all of the layers, until you get from the you go from the left all the way to the right. And there is a video on it as well, which is this one. If you want to learn the intuition a bit better, without me having to go into detail, I recommend watching that video because it's all animated and it shows you a really nice way how to do it, how it's done in a fully connected neural network. Doesn't cover CNNs, but I will cover CNNs for you today. So in order to go from a feed-forward neural network, so this is called a feed-forward neural network, where every node in each layer is connected to the next layer. And then the layer that is not the input or output node, those layers are called hidden layers. And if once you start having a lot of hidden layers, that's when you have a deep neural network. We call that a DNN. I like to call this fully connected neural networks, or FCNN, or dense networks as well. That's fully connected dense neural networks. So when you're working with TensorFlow API, like the layers API, in the layers API, there is a layer called dense. That's what each of these layers are called. So whenever you want to create a fully connected neural network, you use a dense layer. All good so far? Any questions? Perfect. So let's try this. So let's use images and pass images through a neural network. All right. So, for us to understand how to do that, so you might have been passing numbers or whatever from the input layer through the network. How do you pass images through the network? So images are basically array of numbers stored in a computer. So a grayscale image, for instance, is an array of numbers. These numbers range from 0 to 255. 0 represents brightness of black, 0, and 255 represents the maximum brightness in that color channel. So grayscale image only has one color channel, which is gray. No, it's just one of them. But color images have like 3 color channels: red, green, and blue. And depending on how you play around with the brightness of each channel, you can get any color you want. That's literally how your your screens represent, show the images. So computers literally read these array of numbers in a stack, and then they figure out what color that pixel should be. So each coordinate in these stack of matrices represents basically a pixel in your screen. And if that, for example, if that pixel is completely red, that means that the green and the blue channels have 0 in it. And then on the red channel, you have 255. If it's black, every channel, that coordinate has 0 in it. And if it's white, every channel in that coordinate has 255 in it. So this is how images are stored in a computer, right? For you, it's understandable. You look at an image and say, this is an image of a dog. This is an image of a, I don't know, is it a cave? Is it a face or whatever, right? But for computers don't see that. They just see an array of numbers. Like literally try to imagine you don't see anything on the right-hand side. And the only thing you look at is the left-hand side. And you have to figure out what you're looking at. Like at the moment, we don't even know what this image on the left-hand side is. We just know it's just an array of numbers. So this image on the left-hand side is a color image that is 4 by 4, and it has 3 color channels. Now, a big image like your laptop, like if it's a 1080p laptop full HD, it's got like 1080 pixels by 920 pixels. So that's like a lot of pixels. Like if I multiply 1080 multiply 1920, we've got 2,073 pixels right now in the screen. That's how big this image is right now. And this image, every pixel, the position of the pixel and the color of it is a data point that we need to know more about. So every pixel has a relationship with the next pixel, right? So there is a context. And I'll come into that when I talk about why we go from fully connected neural networks to a CNN when we work with images. Any questions around how images are stored in a computer? So this is how images are stored. Videos is another dimension. When you add the dimension of time, you have a video. So when you take 30 images and you put them next to each other, you have 1 second of video. That's a video that is 30 frames per second. So that's a normal camera. So when you put a CCTV camera and then the camera keeps recording, what it's doing is just literally saving a lot of array of numbers, 30 of them per second. So that's literally what that is doing. So videos are basically just an array of images, and images of array of color channels, an array of numbers, a stack of numbers basically. For an RGB color. And in digital computers, you normally use RGB. You don't use other types of color channels. You might use hue as well, which is HCG, I think. Hue, saturation, and brightness, HCB, which is another way of defining your image. You might also use CMYK, which is another type of like color channel, normally used in printing. Normally graphic designers use that, but in data science and like in computer science, we normally use RGB. And having a grayscale image or a color image, it changes like what your data is. So if you don't have the colors, you lose context in the data. It's like try to convert an image of a cat or a dog into grayscale. Like it might become harder to identify the cat and the dog if the image is not very understandable. Any questions? That's good. So that's how images are. And so we have a question from Yao. How are the layers different from each other? Presumably it's a type of function used in that layer. Are you talking about the neural network? Oh. The layers are the same. So each layer here, for example, has the same number of nodes. It's just that like there is some connections from the input layer to that layer and then from that layer to the next layer. I'll go into how DNNs work in my previous workshop, so I'll post a recording for that. But basically, it's just think of these deep neural networks as a safe where there is an input connection and an output connection. And then you have lots of knobs and dials on it. And then you just basically try to play around with these knobs and dials until the input maps to the output. That's basically what a neural network is. So your function is literally built based on this. So the more layers you have, the more knobs and dials you have that you can play with. And the knobs and dials are literally these weights on the connections. So each of these lines is a weight. There might be also biases as well. And then you just play around with, and then your algorithm or your optimizer basically tries to play around with these weights and biases, updates them in each step until it's all connected. So in a convolutional neural network or in a fully connected neural network, what happens when you go from left to right is that as the image is processed through the network or is feed forward to the network from left to right, it basically, the network starts to learn features of that image. And those features starting from simple all the way to the complex. So for example, in the first few layers, the network will see like on all the vertical edges, all the horizontal edges, all the like diagonal edges in the image. And then in the middle layers of the network, it puts these edges together and like constructs shapes like rectangles, circles, triangles, or whatever. And then it puts those together again in the image until it gets into more complex features like, I don't know, a nose or a ear. And then it puts those together to figure out if it's looking at a cat or a dog or whatever. It could be anything else in like other types of images. So for example, you could build it to recognize different types of bicycles and then classify bicycles and its models based on just the looks of the bicycle. So one exercise could be, for example, if you can find a lot of images of bicycles that have like names and models, you can actually train a neural network to like classify different types of bicycles by just like passing it an image of a bicycle. So in a fully connected layer for like this one, if you pass the image through this fully connected layer, what you would see is in the first few layers, you could identify the light and dark pixel values. Then you identify the edges, and then you identify a combination of edges. Then you identify features, and then at the end, you combine these features together to identify who is it that you're looking at? Who does this picture belongs to? Like, for example, if you're doing face detection, you could train a fully connected neural network to do like a simple face detection. The only thing you need to know is that the input layers, it needs to be the same number of, so the number of nodes in the input layer needs to match the size of the image. So if the image is 24 pixels by 24 pixels, you literally do a math and figure out that you need 576 pixels. So you flatten the image through the first layer. So you take the array of numbers and then you just basically flatten it into a list of numbers, and then you pass the list into the network. And then at the end, the output layer is number of classes that you have. So if you have 4 classes like George, Ali, Michael, or 3 classes like George, Ali, Michael, let's say 4 classes, George, Ali, Michael, I don't know, Michelangelo, and then 3 classes, George, Ali, Michael. Or you could have like 1 class, or other things, for example. You could have a 0, 1 type of output. It's called a binary output. So in that case, you only have 1 node at the end. If it's true, it outputs 1. If it's not true, it outputs 0. And you can train the network on that. So you could have a network that trains on, is this Ali or not Ali? Is this Ali or not Ali? And that's it. So that's a binary classification task. This one is a multi-class classification task. Any questions? So as the network learns, you see like different links start becoming thicker and other links start becoming thinner. That's when your neural network starts to learn. So some weights So the links represent the weights of the neural network. Some weights become really big and some weights become really small. The ones that are big are the thicker connections. So remember when I talked about the brain cells, the brain pathways, the more you learn a skill, the more certain pathways become like wired together and like thicker. This is the same like representation mathematically. All right. So what we're going to do now is, before I go forward, does anyone have any questions? So this is all the conceptual parts that I wanted you to know. I'm going to cover TensorFlow now, and we're going to actually build this together, like literally this network you see here. But instead of passing the, I don't know, image of George, we're going to pass in images of clothes, like small images of clothes, 16 by 16 pixel in grayscale. Oops. Any questions? So in principle, the layers are fully connected, but some weights can be close to zero. Exactly. So one of the things I'm going to cover as well is we need to keep the weights around zero. So the weight shouldn't be like 1, 2, 3, 4, 5, 6, or like, sorry, 2, 2, 3, 4, 5, 6, or whatever other number. The more the numbers are closer to zero, the easier it is for your network to converge to a solution. Otherwise, your weights could explode. This is where you've heard of exploding gradients. So your weights could explode and your network would never learn anything if the numbers are not close to zero. So there is some intuition to learn about how to architect your neural networks, and like the intuition around the maths of it mostly. That's why like most courses try to teach you the math so that you understand like the intuition around what happens to these numbers as the neural network trains. All right. So basically, so this is how it works. Now, if you want to implement this now in a computer, in a program, in Python, we have a framework or a library called TensorFlow. I don't know if you've heard of it. It's quite popular, but for just completeness, I will show you wherever you can find the library. This is the website for it. So TensorFlow is a production-ready framework for machine learning, basically. You can literally train, analyze, process all your data through, and create a model and deploy it with just TensorFlow. Right? It's a library developed by Google. It's more, in my opinion, it's better for production apps compared to PyTorch. PyTorch is better when you are more doing academic studies and research, because you have more control over the whole process. With TensorFlow, it abstracts away some parts of the training process from you. So you just focus on the architecture and like some other bits of the training process. With PyTorch, you literally have to build the whole process yourself. But it's more Pythonic. You can debug it if things go wrong. So it's easier to debug compared to TensorFlow. So it depends on like your preference. I'm gonna teach TensorFlow just because it's mostly used in the industry, right? And TensorFlow uses a specialized data structure called the tensor. And just think of a tensor as a wrapper around lists and NumPy arrays. So you have a NumPy array if you work with the NumPy library. So in NumPy library, you could take a number, package it up into a list or into an array and call it a vector. And then you can package your vectors into an array of numbers, call them a matrix. And you could just keep going on and have a stack of matrices and just go higher in dimensions. What a tensor does is that is a type of data structure similar to a NumPy array. It's literally like has the same operations as NumPy arrays. So if you learn NumPy library well, and you know all the operations around like how to multiply matrices together and linear algebra and all those things, it's literally the same with tensors. However, the only special thing about tensors is that they are optimized for computations like that are very parallel and very large. So we have a thing called tensor ranking, which is similar to this. When you take your numbers and you package them up into like lists, then like matrices, and then basically stacks of matrices, and then box of stacks, and then boxes of boxes. You get this like n-dimensional tensor that is like loads and loads of numbers in it. And then what you could do is you could take these and then you could literally multiply all of them together in graphic processor units or GPUs, all in parallel. So you do a lot of maths and you do a lot of multiplications all at the same time using linear algebra by just taking all of these tensors and then putting them on that. So like, for example, when you train a neural network, instead of like doing every update of every weight one by one, you literally put all the weights in a big, massive, like n-dimensional tensor. And then you just basically do the updates on these tensors all in parallel and then multiply them all together, whatever. Because you need to do a lot of multiplications, remember? Like for each node, you have to like multiply things and sum them all up. And with tensors, you can literally do that all in parallel. And that's why like it's way, way faster to train complex neural networks with lots and lots of layers on GPUs in like a couple of days. Even with this, like some neural networks that are very deep, like for example, they have 60 layers, right? They could take a week to learn. Like you need to pass them 10,000 images over like, I don't know, 100 epochs, 500 epochs or whatever, 50 epochs. So each epoch representing the number of time you go over the whole data set. And it would take a week to train on a GPU. There's just like how many calculations like the algorithm needs to go through to train that model. So with TensorFlow, you literally need to use that's why TensorFlow implements this data structure called tensors. You cannot train anything without tensors. So you need to actually convert your data into tensors before you can do anything with it. And in TensorFlow version 1, you actually had to fiddle around with something called the computation graph, which is just a way for TensorFlow to optimize your Python code. So it would construct something called a graph of your Python computation, like how your functions link to each other and how data passes through them. But these days, you can actually debug your code in TensorFlow using something called an eager execution. So it's more Pythonic now these days, compared to the version 1, which is like you have to fiddle around with like low-level stuff like the computation graph. But think of TensorFlow as like this library that like super optimizes everything and like parallelizes everything when it comes to neural network training. And it does that on GPUs these days, but now that Google has another thing called the TPU. So if we take the unit of calculation, like computational power as a gigaflop, like some of the latest GPUs are around 15 to 20 gigaflops, but like Google has made something called the tensor processing unit, which is like around 40 gigaflops, right? So that's a lot of gigaflops. And yeah, so basically based on that, then you can literally like do things way faster. And you actually have access to this as well. So if you go to that Google Colab link I sent you, I think you can set the runtime. So change the runtime type to TPU. So you can learn more about it here. So you can change the runtime type to TPU and it runs super fast. But GPU for our application is enough, right? You don't need TPU on much time. Today's session will be recorded and previous session will also be recorded and uploaded. We will send you the link. So I know you've provided me emails, and when you registered, I will send you basically an email with the link to the slides, resources. All right. Any questions? All right, so before I show you any code, I need to help you understand how to write the code. So every TensorFlow program that you will see, or you will come across, there is a flow to it. There is a common pattern. And that common pattern is this. Basically, you can literally train and build a neural network, or at least a fully connected network, in 15 lines of code, just like this, right? And I'm going to break down each line for you so you understand how it happens. And once we do that, then we can actually learn how to build our own CNNs as well, right? There are two ways to build your network. There is like something called a sequential API, where you just basically put a list of layers, pass it to the sequential class in Keras. And there is a class API where you have to create your own class. And then in your own class, you need to define two functions. One is the init function that has a super that basically inherits the tf.keras.model. And then in here, you basically line by line, you define each layer of your network. And then you call that in the call method, or and then you need to do a TF gradient to update. This is like a more advanced version. But normally you will be okay with just doing the sequential API. So in most of the cases, you would be able to actually build most of the popular CNN architectures with just using the sequential API. And Keras is the library that allows you to build these networks. What TensorFlow has done is TensorFlow has come up and taken, like, wrapped itself around Keras. So Keras has like an API that helps you build lots of like these neural network applications. And then TensorFlow comes and wraps itself around it and adds lots of functionality on top. For example, MLOps, like deployment functionality, improving the calculations, like metrics, things like that. And so it's just like a massive wrapper around Keras that allows Keras to be extended further and do more things. For example, data processing, piping data through things, I don't know, like more efficient computations, things like that. So that's what TensorFlow has done. So that's why you always do tf.keras, because Keras is now a part of TensorFlow. But you can also install Keras separately if you don't want to deal with TensorFlow whatsoever. Ernest has a question which says, is the GPU on PC any good, or do we have to get external GPU? No, any GPU is GPU. So as long as normally, I think most of the GPUs that like TensorFlow and current libraries support are NVIDIA GPUs. So I don't think AMD works. So TensorFlow normally so the same code here could run on the GPU, and like you literally just run this, and then TensorFlow will figure out if you have a GPU or not. If it's installed and like configured properly, then you don't need to do anything. So TensorFlow will like when you run this code to train the model, if you have the GPU, TensorFlow will just run it on the GPU. And normally NVIDIA GPUs are doing that. And I think Apple Silicon M1 Max, I don't know about those, but I don't think they are supported by TensorFlow, unfortunately. There may be like some Python libraries that allow you to work with them. But the best way to do it is just run the code I give you and then see if there are any outputs in the terminal telling you that it's using GPU. Easiest way to do it is if you're doing experiments, the best thing to do is just do it in Colab, like open a Colab and then just like try to play with your code here. You have a GPU. And then once you're happy with it, then you can go back and try to figure out, once you've done the debugging and everything and make sure your code works, then you can go back and figure out how you can then run it locally on the GPU or run it on the cloud on a GPU. But this is one of the easiest ways to like get access to a free GPU. But like the problem with this is that you cannot actually train like commercial level neural networks on these, because the runtime of Colab is quite small. Like I think it kills your notebook after an hour or two of training. So normally you only use it to just test stuff and experiment. You can't actually use it to train stuff. All right. So let's get into the flow. So the first thing you do in TensorFlow is you prepare your data set. Now, TensorFlow has a datasets module, and in here there are a bunch of like, so if I just go to TensorFlow API and just search data set, you have all of these like lots of different data sets like C410, Fashion, MNIST, IMDb, I don't know, MNIST data. So you can literally like load them in and play with them. It returns two tuples, and each tuple contains a train images, train labels, test images, and test labels. So the train images is like a list of images. There are about 60,000 train images in the Fashion MNIST. And train labels is a list of numbers, basically, representing the index class of the label. And same thing with test images, there are about 10,000, and then there are 10,000 test labels as well. So if you just do this, it loads the data. And then what you need to do is normalize that before you pass it through the network. And then you go forward. And then just to give you an idea what the data, what Fashion MNIST is, it's literally, no, it's not this one. Fashion MNIST is this data set, right? So label 0 represents t-shirt, label 1 represents trouser, 2 pullover, and this is what the data set looks like very tiny images, all grayscale, like they are like 28 by 28. Mostly they are, this is this data set and the MNIST data set. They are more research level data sets that are used to benchmark like algorithms and like performance of neural networks, things like that. So a lot of researchers use this, and they are also easier to teach because they're very simple data sets. More complex data sets are those that are like lots of classes like this one, and lots of different, like the images are a bit bigger. Like this is even still a simpler data set, although it's color, there are more channels to it, and there are more labels, there are more classes, sorry. The images are quite small. I think this is still like 16 by 16 or something. It's when you have to use like your own images and stuff like that is when it gets complex. And that's then normally when you need proper cloud computing level stuff.
Allows the school to focus.
Right. So when you load your images in, the next thing you want to do is you want to normalize both your train images and test images. And the only way to do that is just divide the images by 255. So 255 is remember the images are 0 and 2. Every number in an image, in an array of numbers, is between 0 and 255. So when you divide by 255, we normalize it. Does anyone know why we normalize images before we pass them to the neural network to train? Silence. No one knows? So the reason you normalize your image by dividing it by the maximum value. So the images are an array of numbers, and then the numbers in that array, the maximum value of that number is 255. When you divide by 0, you normalize the distribution of the numbers around 0. So imagine a distribution, and then the distribution could be away from 0. When you divide by 255, you bring the distribution on the 0. So you center it on 0. And the reason you do that is because then when you do all the multiplications, your loss function before you normalize, right? Your loss function before you normalize could be very skewed, looking like this one. And then when you normalize, it becomes like a bowl shape, and it's much easier for the neural network to converge. So when you do gradient descent, and then you go down the loss function, if your loss function is skewed, your learning steps, so as you start training, it could bounce around like a crazy ball, like, you know, like when you shoot the ball down the valley and then the valley is like very deep. It could bounce around and like takes ages to converge. But with a normalized function, it will take smaller time to converge, basically. Right? Just if I will have to ask people to just mute yourself while I'll talk, so it doesn't distract people. So that's why you have to normalize. So if you don't normalize your loss functions, remember you're doing a lot of calculations, right? So you're doing a lot of math. So if I go back to this slide where you have the maths bits, So if you don't normalize your image, your input, when they get multiplied by these weights, as soon as your image gets to the next layers, it starts to explode. The numbers like start to become really big. Like you start to multiply, like let's say 10 by 0.5, and then you multiply that by another number, and then you multiply that by another number, and like go on. Like it becomes really big. You know, like as soon as you start multiplying by big, like your numbers could explode. Right? It could explode, and this is what we call a exploding gradient problem, where like in a gradient descent step, it just never converges, just bounces around. So that's why you normalize your images, to help you with to help your algorithm to reach convergence faster. All right, Ryan, I'll take on your offer, so I'll make you host as well. So in like oh, I can only change host. I don't think I can make you co-host. Yeah, I can't make you co-host. I'll just have to change the hosting. Yeah, sorry, I can't do it. So LPMB says, any rules on how to divide the data set into training set versus test set? Does it depend on the size of the data? So I think that's something we will cover in the next session, into where we how to do it. But yeah, there is a way. I think scikit-learn provides some functions. So if I just search scikit-learn, I think it's called split. Model selection, shuffle split. So you see all the train test split, you can use this function to do it. So train test split is the function you want to use. So you pass it basically your images, and then it basically splits them for you. So X is your array of images, Y is your array of labels, and then it splits them into a test size of 33%, and random state is just the number you pass it. And then it randomly creates your X train, X test, Y train, Y test. So if you want to do your images, you can use the scikit-learn model selection train test split function to do that. With this, it's already split for you. And then here is where you create your model. So you use the sequential API, and then you pass it a list. And then in this list, the order matters. So you start with the first input layer, then this next layer, and then the next layer. So here, the input layer is a flattened layer. So you flatten the image, and then the input shape of the image is 28 by 28. So this is what you need to define. You need to tell it what the size of the image is. If you want the TensorFlow to figure out the image size itself, you can pass none, a tuple of none as the first image. And here you can also pass if you have a color image, you have to pass 28, 28 free, which represents 3 color channels. So 28 multiply 28 multiply 3. So that's a layer node, a flattened layer that is 2,352 nodes long. Then the next layer is 128 nodes in it. We use the ReLU activation functions, which is the standard activation functions we use to add nonlinearity. So that activation function, basically any number below 0, it just sets it to 0. That's what it does. And any number above 0, it doesn't touch it. So that this way it adds some nonlinearity to the neural network. So your function can do like curly stuff as well. It wouldn't remain linear anymore. And then at the end, we have a dense layer that is 10 nodes in it. So remember, we have a 28 by 28. So the first layer is 784 nodes. The second layer is 128 nodes. And it's a hidden layer. And then the third layer is 10 nodes. It's because we have 10 classes, remember? So if I go back to the fashion MNIST, we have 10 labels. 0 to 9, it's 10 labels. That's why the last layer, you need 10 output nodes. Each node represents that specific label. So we expect each node to output a number between 0 and 100. 100 means confidence. So probability that the neural network thinks this it's looking at an ankle boot, or it's looking at a like a t-shirt or something like that. So the predictions of your neural network is basically an array of predictions, and the position of the number in the predictions array is basically corresponds to the label. So I will show you that basically. And then at the end, here we pass the 28 by 28. So we set the image size to 28. And then you need to build the model using model.build, and then you tell it what the input shape of the model is. So here is a one color channel, image size, right? And then you compile it. And then when you compile models, you always pass the optimizer, the loss function that you will need to use, and then the metrics that you want to use to evaluate your model. So we're going to use an accuracy to evaluate the model. The loss, we're going to use a sparse categorical and cross entropy. So this is what you use when you are doing classification. You use a sparse categorical cross entropy, and sparse categorical because we have more than one label, we have more than one class. If it was only one class, like yes or no, you would use a binary cross entropy, not a sparse categorical. And then from logits means basically like, because this one, we don't have any softmax function at the end, we do from logits to like make it into probability distribution at the end. Optimizer, we use ADAM, which stands for adaptive moment. So moment is like, you know, when you do gradient descent and like the ball is going down the hill, we can actually play around with the acceleration of the ball. So like, and when it's at the top, we can make the acceleration go really fast. And then when it gets to the bottom, the acceleration could slow down. So like the ball converges. Otherwise the ball overshoots. So ADAM can do that. It can play around with the moment, which is acceleration of the ball going down the hill when it's trying to reduce the loss function. So we compile the model after we build it. So we first define the architecture, then we build it, then we compile it. And then we use the .fit method to train it. And then all you have to do is basically pass the images and the labels to train. And then the number of epochs represents how many times you need to go over all of the, images, all of the train images to train. So if you train like 10 times over all of the images and you still feel like there is more to train, you could change the number of epochs to more. This is one of the hyperparameters you play with alongside the architecture of your network and how many nodes in each layer should have. These are all the different types of hyperparameters you can play with to map your input data to your output. And then at the end, you do a model that evaluates, which then you pass your test sets and test labels to. And then if you want the output to be more verbose, you can set the verbose to 2. You get a loss and an accuracy. These are scalar values. And then once you're happy with your model, you can do model.predict. You pass your test images. So this is an array of images. This is a list of images, sorry. So a list of stacks of numbers, basically. And then your output will be a list of lists. So each list represents the probability distribution for each label. Or for each label in each image. So if you pass in like 64 images, you get 64 lists. And then in each list, there are 10 numbers. Each number represents the confidence for each label. And then at the end, you can create a folder. And then if that folder doesn't exist, you create it. If it exists, it ignores this line. And then you do a model that's saved. You save your model in that folder. And then you can then load it back using Keras models, load model, and then you load that model in. And then you make the predictions on it. So that's how you do it. I can show you a good demo here. So I have the code written here for you that does that. So when I run this code, this is what the output looks like. So you see, we've got 100, 1,000 parameters in this neural network. All of them are trainable. And then we go over all of the training images 10 times. And you can see the accuracy has started going up from 77% all the way to 87, 88. And then it looks like we've hit a ceiling of 88% as the accuracy. And then this is one of the predictions that we output. So do you see these predictions that are like an array of numbers? Like this is a very small predict, like this is nearly 0, right? But this one is nearly a bit bigger than 0. So it thinks that this image, everything, all of the other labels are near 0 except this one, which is the biggest. So what is that? If you go back to here, the last label is ankle boot. So it believes that the first image is an ankle boot because this last label is near, it's basically about 100%. So what you could do is, when instead of printing output, you could do np.argmax. So just give you the label for the last item. So if I run this again, it would tell us what are the labels in those images we pass it. So let it train again. So you can actually play around with the code yourself as well. You've got the repo. Oh, sorry, I should have done, let me put a breakpoint here so that I can show you some stuff. Let it train again. So as you can see, like most of the time we're stuck at 85%. We can't get above it. We can play around with the architecture and the other hyperparameters, but the problem is there is a hidden ceiling when you work with fully connected networks when it comes to images. That's why, like in the second part of the workshop, we're going to cover the other ones. So the output is 10,000 images that are the test images, and each of these 10,000 images are basically 10 numbers in them. So if I open these, you see all of these lists, right? And let's look at the first image. So the first of the test images, if we open them up and I look at them, let's see what we find it looks like. So what does this look like to you? Let's go back to here. It looks like one of these, right? So it looks like a ankle boot, number 9. So the first image of the test set looks like an ankle boot, as you see, right? So if I go back to my console, what I could do is I have the output. I could take the first one. Sorry, in my debug. If I go to the console in here, I could take the first output, the first prediction. So this is what inside the prediction looks like. If I import NumPy as NP, so this is a list of the predictions, probabilities for each label. And then basically all you have to do is do an argmax and then pass the output of the first prediction to it. And you see the last one is a 9. So 9 is the class label for that image, which is an ankle boot. So the first image is an ankle boot. Let's look at the second image and see what the second image is. So we see give us the position of the label that has the highest confidence rate. So this one is 2. So let's look at the second image. The second image in the test set is this one. Let's look at that. Let's see what this is. This looks like a t-shirt, right? So let's look at the second. Oh, it's a pullover. So it has predicted that this is a pullover. Does it make sense? or have I lost you? So we have some questions. All right, so Kaveh asks, can you control Adam? Yeah, of course, we can always control Adam. We can also control Eve. Where is Adam? Adam, let me close all of this, too much. So I think in here, in the optimizer, you can control the optimizer. So instead of passing only the Adam, you actually pass, if I go to TensorFlow documentation and I search Adam, you can basically construct Adam with any of the like parameters that you want. And then you pass this to the optimizer. You pass the instantiation of the Adam class to the optimizer instead of a string Adam. That's what you could do if you want to customize the Adam. Yao asks, does this mean we have 3 layers, 1 input, 1 hidden, 1 output? Exactly. If you want to play around with the input, all you can do is literally just like copy this a couple of times and then just be like, this is like, I'll make this 64, I'll make this another 64, and I like this too. So now we have like 4 hidden layers instead of 1. This is how you can play around with the architecture. And if you see here, I added the last layer, a softmax layer. This is because the predictions are raw predictions. And in order to convert those raw predictions into probability distribution, we call these raw predictions logits. In order to convert them to probability distribution, we need to pass them through one last layer called the softmax activation layer. There is more about it here if you want to read it. That's why we need a softmax function at the end. Logits typically become an input into a softmax function, and it generates a vector of normalized probabilities with 1 value for each possible class. Wow, guys, I was planning to give you a break at 7. It's already 7:15. I imagine that we're gonna go run over time, but that's good. We're just gonna break this workshop into as many as we need. But I hope you understood how images are passed through fully connected neural networks. Any questions before we go for a break? And then after this, we're going to go into convolutional neural networks and why they could be better for image classification or any other kind of images. Any questions? Just put them in the chat or ask. All right, so let's take a break. Let's take a 5-minute break. And then if you want to get some coffee or something, you can come back. Let's come back around 7:20, and then we can continue with the rest of the workshop. Before we go, Kaveh asked, just wondering if you cover filtering at some other point, cluster of setup numbers and edges. Filtering. Do you mean like convolutional filters, Kaveh? Like, yeah, I will cover filtering. They're called filters or kernels. So that is part of it. Yeah, I will cover them as well. All right, see you guys in 5 minutes. Let me share my screen as well. All right, so I'll just need to go in here and then change the sharing settings just to make sure that. Yeah, you should be able to share the link, but I'll just post it into the chat again for anyone who wants to access it. All right. Yeah, does anyone have any questions? All right. So Let's focus on why we want to use a convolutional neural network instead of a fully connected neural network. Does anyone have any idea why we wanted to do that? Why would you want to go and use a CNN instead of a fully connected network? Seems like fully connected network seems like to be doing well, 80%. Why would you want to go and change it to a fully connected, sorry, to a CNN? To understand that, let's look at a cat image. Yeah, why not? We love cats. So what do you think will make the computer understand that this is a cat? Like, understand, imagine that we're looking at this cat, but instead of seeing the cat, you see a lot of numbers, right? So you see an array of numbers instead of a cat. And remember, this is a color image, so you see a stack of numbers, right? So there is a lot of dimensionality in this data, but remember, as I said, the position of each number next to each other. So if I zoom here and look at the pixel here, like the pixels of the location of the ear and where it is in the image in relation to the eye and in relation to the nose, these are very important. When you flatten the image to pass it through the neural network, you lose all this information. You lose all the context around what the image is. So when you convert this image into a fully dense network and you pass it through a fully connected network, with simple data sets like MNIST fashion, it might work because maybe it can figure out how to use that flattened array of numbers to map an image to the output. But with more complex images, you lose this context and you lose this dimensionality of the data that you don't necessarily have with when you use a convolutional neural network. Because what convolutional neural networks do is they don't actually flatten your image at all. They don't touch your image in terms of flattening it and making it lose this context. What they do instead is they create a lot of Instagram filters, I would like to call them. So they would create a lot of convolutional layers. Think of them as like Instagram filters. You know, when you go on Instagram and like you set filters, and like one filter is like, I don't know, it's got like sepia applied to another filter, it's like some other thing applied to it, it enhances the image and things like that. It's similar to that. And we use something called a kernel to do that. So think of a kernel as a 3x3 grid that like passes over the image and convolves a part of the image into one pixel. So if the input image is the one at the bottom, the kernel passes over the image and slides across like this. And for each part of the image, it basically convolves that part of the image into one single pixel value. So 9 pixel values become 1 pixel value in the output image, right? So normally you also can use paddings to make sure that your input image, so the dashed lines outside are the paddings. So padding images, they could set them to 0 or 255 to make sure that your output image is same as input image. But normally when you convolve images like this, you lose your size starts to become a bit smaller. So that's why you add padding to make sure that you have the same image size at the output level. And in terms of the mathematics, this is how the mathematics work. So as you pass the kernel, so this is our kernel. So we have a kernel or a filter that looks like this. And then basically as you pass it across the image, the numbers get multiplied and then all added up into one single value, as you see here, right? So this way you convolve one image into another image, into a smaller image. And that way, this is how a neural network, a convolutional neural network like this, creates these filters, as you can see, creates these images, layers in each layer, and learns the features. So for example, the beginning layers learn all the edges that are vertical, horizontal, and diagonal. The next layer learns like how these edges come together to create shapes. And then the next layer learns how these shapes come together to create patterns, for example, the cat's ear or the cat's nose. And then the last layer figures out how those patterns come together to create like an object. So you use this convolutional layers, convolutional operations to basically extract the features. So we call this a feature extraction operation to extract the features into the next layer. And if you want to get more intuition around it, this is an example. This is a really good website on it called Setosa. I'll just show it to you. So this is a kernel that you see here, and that's your image on the left-hand side, right? And then the computers see this image on the right-hand side like this, right? So imagine you don't see the image on the right-hand side. This is what the computers see. So you see how hard it is to figure out what you're looking at if you're just a computer. So that's why like we need to like use convolutions and mathematical operations in order to in order to be able to extract features out from the image and reduce the dimensionality of the data. So this is what the convolutional neural network does. It literally basically, you can play around with this website and understand how image kernels work. Basically, you take a kernel, here is a 3x3 kernel, and you have different types of kernels. We have a blur kernel that looks like this. We have a bottom swivel kernel, left swivel kernel. So left swivel basically helps the output image to detect only the left edges that are moved, that are towards the left. You have like other types of kernels like sharpen, that sharpens the image. So when you convolve an image using these different filters, like the identity kernel doesn't do anything. So the identity kernel looks like this. When you convolve the image using these filters, you get a new type of image. And I like to call it like Instagram filters. You create a separate, you basically apply a filter to that image and you create a new image from that. And then using this, for example, you can take a high dimensional image like the left-hand side and then convolve it using this filter into an image like the right-hand side that loses all the other noise and only keeps the information. And the information here is the edges of the, for example, of this object in the view, right? So we have like different types of kernels. We have identity kernel, we have edge detection kernel. So like these, some kernels are used for sharpening the image. Some kernels are used for detecting the edges. Some kernels are used to like just move past the image from one convolutional layer to the next. And then depending on how you put numbers in these kernels, different images are outputted. So when you design your convolutional neural networks, like the neural networks could basically learn to detect patterns. It plays around with the kernel values. That's why we call it this. The kernel values are now the weights, right? So previously the weights were the connections between the nodes. Now the weights are the kernel values. So now the neural network, you can define as many kernels as you want, and it creates as many filters as you need and as many images as you need in each layer. And then you basically, it then trains the network on these kernel values to figure out how it needs to create these filters in order to pass from the left-hand side all the way to the right-hand side, right? And when you create these edges in the image, all of these edges are information in the image. And the way you look at the image gradient and the edges is basically any values. So in an image, any pixel that has a higher value, like 255, it's a white pixel. Any other pixel that has a darker value, that is near 0, it's dark. And the gradient of the image is defined as you moving from dark to light, right? So these edges that you see, basically this kernel detects where the pixel intensities change, and it basically creates that's how it detects where the edges are and produces the edges this way by looking at the pixel values and how those pixel values are changing. So as you convolve the image using this operation, you detect the edges, and these edges are actually the actual signal in the noise, which is the whole image. So if the whole image is a signal plus noise, you take away the noise, and then you just keep the signal, which is just the edges, for example. Wow, lots of questions. So before I go forward, let's answer some questions. So correct me if I'm wrong, App Hipsa, I don't know how I pronounce it right, asks fully connected networks just captures 1D data information from the input, while CNNs capture ND data from information. That is correct. So if you look at TensorFlow, yeah, we have conv, if I just search conv, we have conv 1D, we have conv 2D, and we have conv 3D. So 3D is, for example, for like image X-ray scans, where you also have like time dimension or like other types of dimension in your data. And you need to use all of those dimensions in there as well. So you can actually convolve across time too. Gets tricky, right? So, and that's why you want to use any of these convolutional layers. Like you have so many different types of layers, you see, you have transpose layers, but basically the main thing with the conv 2D is that like you just define the number of filters you want to have, your kernel size, and your stride, which is basically how fast or how much you want to move. Do you want to move 1 step at a time or 2 steps at a time? And then what your padding is, things like that. So you can use a conv 2D layer this time in order to convert your fully connected layer to a convolutional layer. And basically kernels let you do that. So kernels allow you to convert your image into filtered images like this one. And you can have as many as you want. So when you define your neural network architecture, you can define how many filtered images you want to have in the next layer. And the values of the kernels is what the neural network then tries to figure out for you. So the more values you have, the more network parameters you have, the more your network is free to learn patterns. So if you feel like your images are very complex, have a deeper network, have more filters in there. More asks, does it need to be 3 by 3? No, it can be anything. You define the kernel size. You see, the kernel size is up to you. You can define it any way you want. Here, for example, the kernel size is a 3 by 3. So when you just pass one number, it means 3 by 3, but it can also be any other size as well. Normally, the kernel size is a tuple or a list of integers. And if we keep to 3 by 3 kernel, does that mean that we need more layers depending on complexity? So the bigger your kernel is, the more the context carries out, but also the more noise you capture. So the smaller the kernel, the less noise you capture, but also you may lose context. So it depends. So normally what happens is in the beginning layers, maybe you want to keep your context as much as possible, but as you go through the network, you may want to like make your kernel smaller and smaller and like make more of those kernels. So in the beginnings, we want to keep the context because you're still playing around with the data and you want to keep as much as the context. So the bigger your kernel size, the more of the input image you capture as you move the kernels across and creating the filtered image. But you also capture a lot of noise. So think of this as like more like a dimensionality reduction operation. And that's why like the convolutional part of your network. So when you have a really deep neural network that's like CNN, the convolutional side of it, and then you add a classifier at the end. The convolutional side of it is called a feature extractor. So reduces the dimension, extracts the features out. How do you decide which kernel size to use? I said, so in the beginning, use bigger kernel sizes, and in the end, use smaller kernel sizes. In the beginning, use lower number of filters. In the end, use higher and bigger image. In the end, use smaller image sizes and higher number of filters. So normally, your typical architecture will look like this. So you start with the image, and then you create a bunch of convolutional layers. It's literally nearly the same size as the image, and it's not that deep. But as you go through the network, your stack of filters become bigger and bigger and deeper, but like the size of each image in that stack is smaller and smaller until you connect a fully connected layer at the end to perform your classification with. So for example, in this one, this is a typical CNN where you have a bunch of CNN layers and you take the image, you convolve it multiple times and you pass it through a couple of layers called max pooling. I'm going to cover that in a minute. And then at the end, you connect a bunch of fully connected layers so that you can then convert this data, convert these features into something you can then classify on. And then you add an output layer of 1,000 nodes. So in here, we have 1,000 classes in the image classification data set. You define the output node in any way you want. You define the output layer in any way you want, depending on your application. And then basically you pass that through a softmax as well to get a probability distribution. So that's what a typical layer looks like. And when you're working with color images, this is basically how it looks like when the kernel passes through your image. So the kernel passes through each color channel. And you can also have like different kernels pass through each color channel as well. You can have the same kernel pass through each color channel. You can also have different kernels pass through each color channel. All right. So that's basically what a typical CNN looks like. Now let's look at what the max pooling layers does. So here you can see that like we create a bunch of filtered images in each layer. So in here we start with let's look at what's happening here. So we start with an input image that's 224 pixels wide, 224 pixels wide as height. And then it's got 3 channels because it's an RGB image. We convolve it into a 224 by 224 filtered images and 64 of them. So there are 64 images now that we have. So we basically use 64 filters. And then we then use 128 filters and we convolve it down to 112 by 112. So we reduce the size of the image. Then we reduce the size of the image again in the next max pooling layer to 56 by 56, 256 kernel images this time, 256 filtered images, then 512 filtered images, and then again we halve the width and height, then again we halve the width and height, all the way to 7 by 7 and 512 filtered images. And then we basically flatten this into a 456 node. So 512 multiply 7 right? Go back. Yeah, so we basically flatten this into a 4056 by 4056, and then we pass it to 1000 at the end. So 456 divided by 512 for 056. You get about 7 by 7. So it's about 8, basically.
Bye, Daddy.
Right. What dictates the number of nodes at the end? Yeah, the number of classes dictate that. So at the end, this last layer, you define that. So depending on what your output is, are you doing a classification problem? Are you doing an object detection problem or SemSeg problem? It depends on what you want to do. So if it's an object classification, it could be the number of classes. If it's a binary classification, it could be just one node. Right? So that's what it is. And if we go to the next slide, the max pooling layer, so you see these red layers in here. So what these red layers do is they basically reduce all the noise by using something called the max pooling. So imagine a kernel of 2 by 2 that goes across the image. It takes 4 pixel values and then just takes the biggest one and then outputs that to the next layer. So this way, and what this is doing is literally halving the size of the image from this size to that size, whilst keeping the signal in the image or the feature. So all the noise is got rid of, all the like redundant pixel values have been gotten rid of, and you still keep the actual image, and you increase the contrast in the image as well at the same time. That's what the max pooling layer does in an intuitive manner when you move it across. So normally it's best practice to after a convolutional layer, you do a max pooling to reduce the image height, because the smaller the image width and height is, the less parameters you have in your neural network. So the best practice is to have a really deep network, but like really small, like as you go deeper and deeper, you reduce the size of the image. So you have less parameters. Otherwise, you might end up with your network not converging, or your network overfitting to your data. Any questions? So given 7 by 7 by 512, what does the 512 represent? So 512 represents the number of filters. So here it should have shown 500, it should have shown like a long stack of filters. I think this image is incorrect. But yeah, it's basically after this max pooling layer, the 14 by 14 is the size of the image, and then that with the width and height of the image. And then when you do a max pooling, you basically divide that by 2, but and you get 7. And so that's a 7 by 7, 512 filters. But the maths here is still wrong, just because 456. So basically what's happening here is then it flattens that image. But instead of 456, I think you should do 7 by 7 by 512. When you flatten it, this is what you get. So this is probably not 512 filters, it's less than that. So if I divide 4T56 by 7 by 7, you should be about 82 filters or 83 filters here, not 512. Because then here, what you're doing is you're flattening this convolutional layer into a list, basically into a fully connected layer. And then you add a hidden layer as well, fully connected hidden layer, and then you pass the last output layer. So do you guys want to know how we can convert this this fully connected neural network into a convolutional neural network? Does anyone is interested in doing that? In code. So to do that, all you need to do is get rid of your flattening operation, right? We don't need a flattening anymore, or maybe move it to the end. So let's take this and move it to the end. It doesn't need an input shape anymore, because all it's going to do is just flatten. And then maybe add another couple of layers here. Maybe add another hidden layer. Call it dense. Let's add a ReLU activation. Or we don't need to actually have an activation. We have a softmax activation here. Let's add 10. Right. So this is 10. Let's get rid of this. So there is a dense layer with a softmax at the end. And then let's do another dense layer of, say, this time. And then let's have like, I don't know, 128 items in there. Right. And then these ones, we get rid of them. We don't need them. What we need to do is we need keras.layers and conv2d. And it's capital, right? And then in here, what you pass is the number of filters you want to create, right? So let's say we want to create 64 filters. And then you can pass the size. You could either pass 3 by 3, or you can pass 3. I'll do 3 by 3, so that's our kernel size. the activation function, and then the input shape, which is basically 28 pixel by 28 pixel by 1 color channel. So you need to define the color channel here. Then in the next one, you apply a max pooling 2D layer, 2 by 2. Then let's add another convolutional layer on 2D. And then let's do 128. And then let's do by 3 again. Activation is ReLU. Let's just copy this. So activation function of this layer is ReLU. And then let's do another max pooling here as well. Layers max pooling. And then let's do a 2 by 2 again. So when you do 2 by 2, it's literally like divides the size of the width and height by 2. So in this one, we divide the size of width and height by 2. That's 14 by 14. After this layer is 7 by 7. And then 7 by 7, 128. 7 by 7 by 128. We get 6,272. Another thing I'm going to do is I'm going to keep the padding the same. So basically what this means is that like add enough padding to the images so that like the output image after the convolution is the same size as the same size as the input. So this convolution layer is not going to change the size of the image. Otherwise it will. So that's why I put the padding the same. So it adds paddings to the end. So if I go back, it adds these paddings to the end so that then when this thing convolves over it, the input output size of this convolutional layer is the same as the input size. So that's what I'm doing here. And then at the end, what I'm going to do is I'm going to add the dense layer. I'm going to flatten it. So when you flatten 128 filters by 7 by 7, this is the number of pixels you get. And then I'm going to pass it to, let's say instead of 128, let's pass it to 1000. And then at the end, pass it to 110. And then basically the rest of the code is the same. Should we train this now? So more, you are very correct. So all of these things you see here, you see these, you define these. These are all your hyperparameters, your kernel size in each layer, your kernel size in each layer, your number of filters in each layer. What's the size of your max pooling layer, and what activation you're going to use, what padding you're going to use. The only things that are set is the output and the input. That's it. The input shape and the output shape, you need to define that set, but the rest is up to you. You can play around with that. So your architecture of your neural network is your hyperparameter. All these hyperparameters, all these parameters you need to define are hyperparameters. And also like these compile process, like what optimizer you use, what loss function you use, and you have a lot of them. Like if I go to the Keras TensorFlow API and I just say loss, this is all of the loss functions. See, you have so many loss functions you can use. Same thing with the metrics. So if I go to TensorFlow API again, and I search metrics, you have so many metrics you can use. Binary cross entropy, hinge, Poisson, I don't know, sparse categorical cross entropy. And then I guess same with optimizers. You have all of these. Add a delta, add a grad, Adam, Adamax, FTRL, NADAM, optimizer, RMS prop, SGD, which is stochastic gradient descent. So you can instantiate any of these classes and then configure them and then pass them to this optimizer class. So, you know, a big, massive amounts of configurations you can do. That's why we have machine learning engineers like literally specializing in this stuff. It's a big body of knowledge. So that's why we're going to cover these one by one over the time. And then the best combination is basically there are So I'm going to cover that now. So the best combination is there are some good architecture neural networks. So there are 5 powerful CNN architectures, LeNet, VGGNet, and Inception, Google Inception, and like Resnet, things like that he can do. So hopefully this code runs. Let's see if it runs now. It's going to take much longer now to calculate. So now we have way more parameters, and that's just because I added too many layers. I could reduce these, but basically now the class ceiling may go away because I now let the network learn the contextual locations of each pixel. Now, looks like I also may need to, because I'm using softmax, I also need to set this to false because I'm not using logits anymore. There you go. That's what this error is about. So now one epoch is taking so long, but you can see we've already at 82%, and we're in our first epoch. And it's gradually climbing. So we just have to like learn it, let it like, go through a lot of more epochs basically. So we see we already are surpassing the fully connected layer performance. But if this was done, if like my laptop currently is like going crazy, like if this was being done on a GPU, it would go way faster. So I have the GPU version open here. So if I just run it, I mean, it takes some time to like load stuff, but let me run everything. Come on, let's compile, model.fit. So all this being instantiated. Oh, I need to set the GPU runtime as well. I forgot to do that. No, it is on GPU. So let's compare it to mine. So mine's running on CPU. Here it's going to run on GPU, and this is also way more complicated, I think. It's using color images. You see how fast it is now on GPU? And it's using color images. I'm running it on literally like grayscale images, and we've already surpassed what's it called, like the grayscale, the fully connected layer network performance. And this is running way faster. It's already like on 4th epoch, and we're still on the 2nd epoch. Whoa, 91% now. I wonder if we can get to like 99. And then I think if you use TPU, it's way probably faster. I can stop it and run on TPU if you want. It's up to you. So let's change the runtime to TPU and run it on that. So while it's doing this, I think because I changed the runtime, I will need to run everything again. So let's import TensorFlow, import the data, import this, model summary, this, and then this, and then this. Let's see how fast it now runs. Interesting. It's not running as fast as I thought on TPU. It might be because there is some kind of like overhead to running it on TPU. Yeah, I don't work with TPUs much, so we'll have to see. Or maybe it's throttled for some reason. Any questions, guys? So you see we have 91% now. We have 3 minutes. We can end it now, or do you guys want to learn a bit more about different architectures that you can use? We can go through like some of the most popular CNN architectures.
Do you have a certificate?
do I have?
You do have a if case. So if case.
Yeah, I didn't understand your question. Maybe like post it in the chat. So I can quickly take you through some of the important architectures. So most of the architectures that you will see literally starts with like big, less number of filters, and then the number of filters keep increasing, and then you get a like very, very long, short in width and height images. And you get to the end where you add fully connected layers and classifiers at the end. So here, I think that the maps will work out. 6 by 6 by 256 is 9216, you see? So this image is correct. So this here, we're flattening it to a fully connected layer at the end. So the training I provide is not like certified or anything like that. It's just basically like me sharing my knowledge. But I am working on putting together a program where you could actually get City and Guilds qualification or like some other kinds of certifications from it. But it will take some time for me to develop the program. So these workshops are just a way for me to just take you through some of the content and improve the content together. So if you find this interesting, yeah, let me know. I have a feedback form in the GitHub repo. There is a link in the GitHub repo at the end here. If you want to provide feedback, you can go there. Oh, the link's broken. I will update this. And then you can provide some feedback, or you can email me. So I'll put my email as well. So if you want to email me with your feedback, feel free. There isn't much left, so I'll just cover these as well quickly. We've got like 2 minutes. So we have 5 powerful CNN architectures that you can also use. Mostly all of them are literally the same in similarities in terms of like you have a bunch of convolutional layers, and then there's a max pooling layer at the end of each, and you get to the end. So with this one, you have basically like about 50, this is like a VGNet. You've got about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You've got about 13 convolutional layers with 5 max pooling layers. And then at the end, you've got some dense, fully connected network with a softmax in order to do a 1000 class classification problem, right? And your images are 224 by 224 color images. You have this one as well. I think this one is GoogleNet or InceptionNet, right? So this is the GoogleNet or InceptionNet. With this one, there is a new type of architecture in there called inception module. So where your previous layer is connected to a 1x1 convolutional layers, and then a 3x3 max pooling layer, and then again 1x1 convolution, right? And then there is some skip connections. So this network is so big that I couldn't fit it into one slide. I had to like cut it into 2 slides. And then you also have like some app layers as well, like middle of the network, where you can actually start outputting stuff as well. So instead of having to go through all of the network to get to the end, you literally get like, you can literally output from the middle. And you also have some skip connections, right? So what the skip connections do is it allows you to convert your loss function that looks like this into a loss function that is smoother. So it allows you to pass the features to the end, and it avoids a problem called a gradient vanishing problem, where when you want to go back and update your gradients, it's just your gradient vanishes through your network. So the deeper your network is, the more your gradient could vanish as it goes through the network. So that's why you add the skip connections in there, in order to make sure that like some of the features and the signal doesn't get lost as it passes through the network, right? This is another one. This is a Resnet, and you can see the skip connections quite a lot as well. And this one is where, I mean, there's a lot of layers in there, isn't it? It's like 34 layers, right? VGG19 is like 19 layers. So with Resnet, you have way more layers. You're always connected to a fully connected layer at the end with an average pooling layer. So this is the only thing that is different. It's using as average pooling. So instead of using max pooling, you use as average pooling, and it's also have a bunch of connected skip connections. So these are like different, more in basically popular architectures you can use. So they're very similar. They have like a feature extractor part, and then they have a classifier part, right? But now you can actually go and implement these yourself. And I recommend you to do that. Like, you know how to create convolutional layers, and you also know how to create max pooling layers. All you need to do is just figure out how to create the skip connections. There is tutorials online, and how to connect each layer to the other ones. Right? So try to see if you can do it yourself to help you learn. And then what we're going to do as well in the future workshops, we're going to cover object detection. So far, we've only covered classification problems. With object detection problem, you will want to actually classify where each object in the image, right? So you want to actually put a bounding box across the object in the image, rather than just using the neural network to tell if an image is a cat or a dog or whatever. And there are different algorithms for that. There is a regional proposals, and there is a YOLO. So we will cover how they work. And then we also will look at semantic segmentation. It's where you actually try to classify every little pixel in this image from the left into classes of, like, if it's which part of which pixels are a person, which pixels are a purse, which pixels are a plant, and so on. So semantic segmentation is way more like complex than object detection, and this just because you have to classify every single pixel into a multi-class problem, right? So 5 minutes over. I hope you guys enjoyed this session. I will post the recordings to the website, and then share you the link. Does anyone have any questions that you want to ask before we end the session? I'll just go through some of the questions we haven't answered. So GitHub repo. Yes, I can share the link again. This is the link. This is still training. Oh my God. Where is the link to the GitHub repo? Oh, I lost it. Interesting. Okay, let me go to GitHub. And let's go to my profile. Let's go down here. There you go. We have other workshops as well. All of the code is in here. So this is the code for the current workshop. Oh, post it to most of everyone. There you go. And other questions. So data capture for ML model, would you advise to collect each individual data point from Google for X and get decent accuracy? So what kind of data capture are you talking about, Api? Yeah, I'm not sure what the question is asking. So to train a neural network, you definitely need quite a lot of images. Wow, guys, 96%. You need quite a lot of images in order to train something to a good accuracy. Like anything above 95% is good accuracy. Wow, we achieved 98% now. Let's see. I have a question regarding what other problems can we apply CNN to? So you just saw a couple of examples. So CNN can be applied to semantic segmentation. They can be applied to object detection. They can also be applied to classification. I've also seen it to be applied into natural language text problems. So maybe like reading text and stuff, or like license plate recognition. That's another thing. It could be applied into tracking problems, like tracking someone through a video. It can also be applied to style transfer, like this example that I showed in the beginning, right? So you can use it to count people. You can use it as, like, for example, detecting where you are in terms of like autonomous cars. You can use it to count people in CCTV cameras, or track people, or count the number of people in a crowd. You can also use it to do style transfer like this one. But there are way more applications. It's up to you to figure out. Like it depends on your data. Like in healthcare, it can be used to classify like people who have brain tumor versus people who don't, using X-ray scans. And I think it can be applied to time series too. I need to check that. But times for anything regarding related time, you may want to use recurrent neural networks. So these are networks can learn sequences in the data. So any sequence information. So time series data is, or text data, because it's sentences, like the way you put nouns and verbs together, they are all sequenced. So whenever your data has some kind of sequence information in it, you want to use RNN. Like with this one, for example, videos could be a sequence of images, so they could have some sequence information in them. If you're going to use videos as a 4D data or 3D data, because you put the images in a stack. So each image is a stack of numbers, and then you stack them together across time. That's like a 3D data point. You can use maybe that in an RNN to, I don't know, do some kind of like tracking, or I don't know what kind of application you can use it for. And then the run hasn't ended. We had 98% so far. How to work with small data sets for text classification. Oh, so the problem of a small data sets, really good question, Shiravan. So small data sets for text classification. Interesting question. So when you have small data sets, you have a problem of underfitting and overfitting. You definitely will have that problem, all right? When you have problems with overfitting, you may want to use regularization methods such as dropouts or batch normalization in your architecture. So there are some batch normalization. So if I go to Tensorflow API again, batch norm. So there are some batch normalization layers you can use in there to help you with making sure that you don't overfit. If you're underfitting, then you want to use data augmentation. So TensorFlow also provides data augmentation. I think it's augmentation methods. Or there are other libraries for that. So there is IMI library that allows you to augmentate your data for machine learning. So what it does, for example, it keeps rotating your data and creates like various loads of augmentations of your data, just so that your model can generalize better. I hope everyone managed to get access to this slide. It is set to public, so anyone can view. I'm going to share the link again. I hope you're able to access it. But yeah, I will send the link after this. So next question. Can you pass the link to previous slides and sessions too? Yeah, obviously, I can definitely do that. I'll have to find that and I will send you the link. Any other questions? So this is used in our mobile phones then, as such as recognizing text in photos. Yeah, Yao, you're right. You probably wouldn't be running something like this on a mobile phone. This is too big to run on a mobile phone. You have like mobile net, for example. There's a mobile net architecture that's like smaller. Like this could be like a mobile net architecture that is like could run on a mobile phone or in the browser. There is also a TensorFlow Playground that I would suggest you look at. So the TensorFlow Playground is really good if you want to get some intuition around neural networks and how they learn. Could you add the slides to GitHub repo? Sure, I will add it right now. Just as you say, as you do it, I'll just be like, here you go, read me, where are you? There, all right. And then basically say slides. You can access the slides here. There you go. Added it. There you go. That's in. Link to the GitHub repo. I think I added it a couple of times, but yeah, I'll add that again. Any other questions regarding the technical bits of the workshop? Otherwise, we can finish the session.
Just for OpenCV as a technology, what's that to do? Is it made of the detection bit he was talking about?
So remember, I said we're gonna do some image processing. So we have we have the sixth session. We're gonna do image processing. OpenCV is the library we're gonna use to do that. Like OpenCV allows you to process images and videos. So videos like MP4.
Oh, so is it like NLTK for NLP pretty much, if you know what I'm trying to say?
NLTK is NLP, yeah. It's nothing to do with
Is it based on that, the pre-processing for NLP problems or something?
Yeah, NLTK is Natural Language Text Processing Library or something. I don't know what it stands for. Toolkit. Yeah, it stands for toolkit. But like if you want to process videos, if you want to run videos through a neural network, you use the OpenCV to read frames one by one, loop over the frames, and then like pass that to the object detector.
Okay, cool.
Yeah. How do you guys think how was the presentation? Did you enjoy it? Is there anything I missed you want me to add? Was it too fast, too slow? How was it?
I think you gave a good layman's representation of it pretty much. You didn't go too complicated, so I appreciate that.
Yeah, yeah, the concepts are complicated, so I didn't want to go into maths, but I wanted to help you understand the intuition more. And we have a 99% accurate model, guys, 99.2. So CNNs are the way to go. Yes, for the maths, I'm going to create some resources, so don't worry about it. But there is deep learning.ai courses that are really good. They're mostly theoretical if you're interested in maths. I prefer more like practical experimental approach like this one, where we first learn the intuition and then you can go into maths later. But yeah, deep learning AI courses is good. There is also a Stanford University CNN course. So if you just search the CNN Stanford, they have a course. I will be creating my own course as well soon on the like basically whole AI deep learning stuff. So keep an eye on that as well. I will email you more about it once I do it.
That's cool.
There you go, guys, 98%. Any other questions? All right. Thank you very much, everyone. We can wait 28 seconds to see what accuracy we get at the end. Otherwise, I wish you a very good evening, and I hope you enjoyed the session. If you have any more feedback, please let me know. I posted my email, and I'll see you guys in the next workshop. It will be arranged in 2 weeks' time. So keep an eye on Eventbrite, follow our page, and yeah, make sure you're on the mailing list. 98.90, guys. Well done. So on the training, we achieved 98%. On the tested, we achieved 92%. So apparently we did overfit a bit. So these are the bits where we have to like look into next in the future workshops. Yao, have you registered through Eventbrite? If you have, you should be on the email list. I will put you on the email list. Perfect. All right. Thank you very much, everyone.